but if somebody else needs to look at it, sorry about that. All right, and B is B sub ij. Notice here I'm making sure that my dimensions of my matrix, my size of my matrix are the same here. Then we'll define the sum of A plus B as a new matrix. So I'm going to give it a different letter here in the middle and talk about how that different letter is defined in terms of the previous letters. So again, I'm just using a small letter here to denote a general entry. I used A and B already, so I just went to C, next letter in the alphabet. But now I need to tell you what C looks like. The reason why I'm making a big deal out of this is because, pardon me, is because we want to use these general entries to help us prove properties later. Okay. So I need to tell you what C sub ij looks like. And you just told me if we use the same premise that you do when you add vectors together, we'll just match components and add them together. Important thing again is though, if I want to take the components and match them together, I need to make sure that I have the same number of components in the same spots, right? I can't mismatch my dimensions. So as a quick example here, if my A is the matrix 3, 1, negative 5, 2, 0, 8, and B is 7, negative 3, negative 2, 1, 8, 5. What do you think we'll get for A plus B? Well, the first thing we should check is make sure they're actually compatible to be able to add. Both matrices here have what dimensions? They're both 2 by 3, right? So I can add them together. So the result is also going to be, bless you, 2 by 3, good. So what's your upper left entry, that 1, 1 entry going to be? 10. The next one across in the row is going to be good. Next one across will be good. What the 2, 1 entry will be 3, and then keep going across. Good. Yeah, good. Again, if you're comfortable adding vectors, then you should be pretty comfortable adding matrices. It's the same concept. As a matter of fact, if you think about taking this rectangular array and just move the rows and put them on the ends, you can just think of a matrix as a big long vector. We can think of these particular matrices, for example, as being a 6-dimensional vector. And before you ask, what's the point of having a 6-dimensional vector? Dr. Olson's husband works for a company that does things with satellites, and they actually represent different things with satellites with six-dimensional vectors and have to work with them. So yes, 6-dimensional vectors actually have practical applications. Okay. All right. In any event, just wanted to mention that just because things seem strange doesn't mean they don't have applications outside of, math class. So, in any event, is that okay? Adding, not too bad, right? How do you think you would subtract? Same way. Yep. If you want to subtract 2 matrices, you do the exact same way. All right. So let's move on then to operations that are a little bit more interesting. And so the first thing we'll talk about is being able to multiply matrices. But there's actually 2 different types of multiplication that we can do with matrices. One of them is probably the first operation that you did with vectors back in calculus, and that was rescaling how long the matrix was. Rescaling how long the vector was, right? Multiply a vector by a constant, call that scalar multiplication. You can do the same thing with matrices. You can do scalar multiplication. So size of the matrix doesn't matter here, right? Because if you think about it, what you did with vectors, you could take a 2-dimensional vector and run a constant through. You could take a 3-dimensional vector and run a constant through. The size didn't matter. You just run the constant through everything, right? So the same thing is going to be true with matrices. Doesn't matter the size of the matrix. I can always run a scalar through. Okay, so if A is the matrix A sub ij, then a scalar, I'll call it K times A, and I know I'm writing it kind of strange, but again, I like to write it this way just for the proofs that we're going to do later. So I make a new matrix. The scalar times the old matrix has the same size, where the general entries are just I take the same scalar and run it through the whole matrix. Just like you would do for a vector. Same concept. So as an example here, pardon me, if you have the matrix, let's do 7, 1, 9, 0, 8, -2, -3, 6, 5. And I ask you what is -3a. What would you tell me? Okay. 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 Oops. If I could write, that would be helpful. Yep. Okay. Yep. Yeah. So again, we're just taking that scalar and running it through every single constant that you, or every single entry that you see in the matrix. Again, just exactly like what you would do if you were running it through a vector. It's just bigger. Okay. All right. So again, those operations pretty straightforward. You can do those operations on your calculator as well, and you would type them in your calculator exactly like you would expect. Let me do it that way. If I go in my matrix here, let's just type in the matrix. We had 7, 1, 9, it's a little 0, 8, -2, I say -3, 6, 5. If I want to do that -3 times A, I can just type in -3, go back in your matrix menu and grab A, and it'll run it through it for you. So you would type the things in your calculator exactly how you would expect to type it in your calculator. Okay. Is okay? All right. So the other type of multiplication that we can talk about is actual matrix multiplication. Now remember when you did vectors, if you've done vectors, when you did vectors back in calculus or done vectors in physics, you defined two different types of vector multiplication. One was a dot product, and we'll talk about dot products later on in the semester. But dot products are inner products where you match up your components and multiply them together and then add it up and you get a scalar at the end. That was a dot product. Okay. You can do the same idea with matrices, but it's not what we want to use for matrix multiplication because we want to be able to use this idea for matrix multiplication with application processes. In particular, if you've got something that has changing in a discrete fashion over time, we refer to that as a Markov process. We can use matrix multiplication to model that process. Don't worry about that right now. But one of the things that we can use matrix multiplication for is to model that process. That dot product idea doesn't help because again, the dot product idea gives you a scalar at the end even matching up entries and multiplying them component-wise doesn't work for what we want. Okay. All right. So when we define matrix multiplication, we do it a little strange. I'm going to do it by example first, and then we will write out the general rule, and we'll do more things along those lines. So let's say we have an example here. Let's say our matrix A is 1, 3, negative 2, 1, 8, 4. And let's say our matrix B, pardon me, is, let's just do 8, 1, 2 as a column. All right, so the first thing that we have to have in order to be able to multiply two matrices together is that we need the same number of columns in the first one to equal the number of rows in the second one, okay? So we have 3 columns here. We have 3 rows here. These have to match. If that doesn't match, you can't multiply the matrices together. Number of columns in the first matrix has to equal number of rows in the second. So notice that if I use that rule, I can multiply A times B in that order, but I can't do B times A. B only has 1 column, A has 2 rows. All right? So A times B is defined, and B times A is not. Okay? So that's the first thing that you notice about a matrix arithmetic property. Well, a real number property is not a matrix multiplication property. You can multiply, oops, sorry, Alex. You can multiply real numbers in either order, right? It doesn't matter. For matrices, it matters. In fact, for matrices, one may be defined and the other isn't. But even if they're both defined, they're not typically equal. So matrix multiplication in general is not commutative. All right, anyway, let's talk about how we match this up. All right, so our first matrix here was a 2 by 3, 2 rows, 3 columns. Our second matrix was a 3 by 1. We said that those inner numbers here that I'm circling in red had to match, right? The end result you end up with is the number of rows of the first one and the number of columns of the second. So your answer will be a 2 by 1 when you're done. Okay? That's how you can tell what the dimensions of the answer will be. Okay? So we're going to get 2 rows and 1 column out of this matrix multiplication when we're done. Here's how we match it up. Now, how we match it up really does look like a dot product. Okay? Remember when you do a dot product of 2 vectors, you match components, multiply them, and add the result? It's really what you're doing here as well. Okay? It's just that the vectors are rotated a little bit. I'm going to take row and match it with column and do a dot product. Okay? So to get this first I'm going row 1, column 1. So to get that first entry, I'll do 1 times 8, 3 times 1, negative 2 times 2, and add it together. Okay? So this will be 1 times 8 plus 3 times 1 plus negative 2 times 2. That's how we, notice I take row 1 of the first one and column 1 of the second one. That's how I get row 1, column 1 of the result. Okay. What do we get for the second entry there? We'll do the 1 times 8 plus 8 times the 1 plus the 4 times the 2. Good. Yep, that's exactly right. That's how we match those things up. 8, 11 minus 4 is 7 for the top entry. 16 and 8 is 24 for the second entry. And again, you can use your calculator to multiply these matrices together. Pardon me. You use your calculator to multiply the matrices together. You would enter the matrices just like you would for every other problem we've done, and then go back and grab it and multiply them together. Like we do for when we did the scalar multiplication idea. So one thing that new that I want to show you today is how we can use other things to help us do calculator type of things. And some of you are in numerical, so have been using R in there. I just want to show you a little bit with R for typing in matrices. Like I mentioned before, when we're using R, we're not going to do anything from a programming standpoint like we've been doing in numerical. We're just going to use it as a giant calculator. Okay. Mainly just to give you a little bit of exposure to it. Later on, we're going to do some least squares idea. If you've had statistics, you've done regression lines, least squares lines. We're going to extend that notion in this class for least squares. And R will help us do some of those calculations rather quickly rather than having to do it by hand. Okay? So that's where we're headed to later on. And also, like I mentioned, we'll compute some stuff later on much more quickly than your calculator will. Okay. So right now, I just want to get the basics down, and then we'll use some of the more advanced functions when we get to that point. But again, from a programming standpoint, I don't expect you to program any of that. And again, the only reason why I'm using R is just to give you a little experience for the different commands. Especially as we're going to try to grab some data and pull it in. R is a pretty standard thing that's used in businesses or in industry. So I figure it doesn't hurt to have a little bit of practice with it. That's my whole goal with this. Not to be a pain. There are certainly other programs that you could use. Unfortunately, Excel is not the nicest one to use for matrix operations, even though it looks like a rectangular array. It's just not the nicest thing to use. You can use it, it's just not fantastic. So anyway, first thing is if I want to type in a matrix, the command is, so I can use anything I want for a variable name, so I'll just call this A. You can use lowercase a, you can use uppercase a, whatever. You can type a word, doesn't have to be a single letter. Okay? Whatever you want to do. As soon as I type the letter and say it's equal to, then it'll store it. You can refer back to it again. Okay. So the command for typing, that's a little bit weird to get matrices entered in here. At least I think it's a little bit weird. Not the first. What the heck just happened? Not the first part. You're going to tell it that you have a matrix coming. So the command is just matrix. Okay. The underlying structure, at least as far as I can tell, as far as R goes, is things are in a list. Okay. To denote that a list is coming, we use the C command. So everything that's going to be in a list is going to be in the C. Okay. So if you want to type in the matrix entries, I need to put it in a list. So I'll use CO of that thing. Okay. All right. Now I promptly don't remember what the matrix is that I typed in before, but I'm just going to type in another one. Let's just say we had the 2x3 matrix. I'll write it on the board here. 2, 8, 4, 3, 1, -2. All right. So one way to put this in here is just type in the entries in a list. 2, 8, 4, 3, 1, 2. And notice that I'm sorry, 3, 1, -2. And notice that I'm separating each one with a comma. So I just have all 6 entries all listed out. I put them in as rows. You could have also put them in as columns, right? You could have done 2, 3, 8, 1, 4, -2. Okay. So there's 2 things that we need to tell R after we type it in. I know it's a little bit clunky, but once we get used to it, it won't be horrible. I have to tell it how many rows there are, because right now I just put everything in a list, right? So the first command, we're going to separate with this with a comma. The first command we're going to put in is, how many rows are there? Well, we said this was a 2x3, so I'm going to tell it it's 2 rows. Okay? So n row equals 2. Now, the default for R is that you are going to type in things by column. So type in column 1, type in column 2, type in column 3. That's not what I did, is it? The reason why I didn't do it that way is because I'm used to reading left to right and then go down. Like we read a book, right? So usually I think type of things in the rows. Okay. So to tell it that I really did put this in rows, the command is by row equals and then true. The default is that by row is false, so we're changing it to true. All right. I want to show you another way that we can enter this, and it might be a little bit simpler, or at least a little bit more straightforward. It's just another command. All right, so once I hit enter, nothing happened, right? I just went to the next line. So if I want to see what A is, I just type in A, and there's the matrix. If you needed to pull out a particular entry in the matrix, you use square brackets and then tell it where it is. So the first entry, the first number is the row number, the second entry is the column number. Right? So if I put it in brackets, then it pulls out what the matrix is. So the 1, 2 entry here was 8. And that's what this notation is trying to tell you as well. Tell you where to go grab it. You can actually rename the columns and rows to different things, but we're not going to do that for our purposes. And we're just going to use them. Like I said, we're just going to use this as a giant calculator for right now. Now, one quirky thing about R is that if I want to multiply it by a scalar, anytime you do multiplication, you actually have to put the multiplication symbol in there, so you need to type the asterisk. If you type 4a, it's going to give you an error to do 4 times a. So you have to use the asterisk. But notice there, it does multiply all of the entries by 4 there. Now, I typed in 4a to get the result. If I wanted to use this, I should have named it something, right? Because it didn't store this anywhere. It just needed the result. If I want to store it for later use, I would have said like b equals that, and then hit B, typed in B to see what the answer was. Okay. We okay with how to enter that? All right. Another way you could enter a matrix. Here it is. Another way you can enter a matrix is using either the what I like to think of as row bind and column bind. It's R bind, C bind. So then that way you don't have to tell it how many rows there are. So if I wanted to type this in by the row, let me just put the matrix in again. I'm going to type in the same matrix. If you use the RBIND command, then I should be able to just type it in as lists of the rows. So the first row was 284, so I put that in a list, separate it with a comma, and put in the second row as a list. And then it knows that the first list is the first row, and the second list is the second row. And then again, I should have come up with the exact same matrix that we had. I just called it a different pattern. If you do it this way, then you avoid having to tell it how many rows there are and that you're doing it by row. Because you're telling it the number of rows by how many things you put in there in the arguments. That might be a little bit easier to enter it in there. You can do the column bind as the same command. So literally the same command. You're just going to type in things by column rather than row. So the first one would be 2, 3. The second one would be 8, 1. I need parentheses. And the third one would be 4, negative 2. Good news is I'm recording this, so if you need to go back and you want to play with it later, you can. Notice I've typed in the exact same matrix 3 times, just 3 different ways. The column bind one is nice if you want to start augmenting things. Maybe you've already typed in a matrix and you want to add an extra column. You can just do the same. So say I wanted to add a 4th column to C, doesn't matter what it is. You can use the same column bind command, C bind. The matrix we used was C to start with, right? And then let's say we want to put another column on here that it has the entries 5, 3. It'll stick that column on the end. So you can start adding things to matrices that way and add on extra columns as you go along. You can do the same thing with row. That's definitely faster than going for your calculator to do it that way. Depends on whether or not you got the computer sitting in front of you, I suppose. Like I said, R is not the end-all be-all for doing linear algebra types of things, obviously. But just giving you an idea of how we can use some computational tools. And like I said, we will use some of the nicer pieces of R to do modeling things later. The whole point. Is okay? Right. The one quirk about R is with matrix multiplication. You'll use a plus sign to do addition. There's not any issues with that. So if you want to do A plus B, it'll do that without any issues, right? If I want to do A minus B, I better get 0 all the way across because it's the same matrix, okay? What's interesting, though, is the way we defined matrix multiplication, I shouldn't be able to do A times B, right? They're both 2 by 3. However, if I just use the multiply command, it will do it. It does it as a dot product, okay? So the regular multiplication symbol is not what we want to use to multiply matrices. Okay? That's the one quarter. The way we have to do it, and I don't have 2 conformal matrices in here, so let me type in one more matrix. I'll call it F. What's that? Yeah, I don't like using E because it stands for a number. So I don't like using E as a variable personally. Let's say I do 1, 2, 3, and I'll tell it has 3 rows. So I'm putting in a 3 by 1 here. I could have just used C bind and typed in 1 column as well. All right, so now I should be able to do A times F, right? A had 3 columns, F has 3 rows. The command is you put percent signs around the multiplication symbol. And then we get the answer that we want. The one quirk for doing matrix multiplication. You have to use percent signs around the multiplication symbol to get it to multiply the matrices together. All right. So we've got 3 different ways that we can enter a matrix. I honestly, if you're want to do things more quickly, I would probably use either the row bind or the column bind command, R bind or C bind. This just seems to be a little bit faster than ever. Remember to type in how many rows there are, and did I type in that big long list by row? And then we've done a little bit with matrix arithmetic. Any questions? And we're going to do more examples here in a minute, but any questions about our commands here? I think it's enough R for today. Like I said, I just want to use it as a giant calculator. Okay? I'm going to do lots of fancy things with it. We'll do a little bit more fancy things later, but we're not going to do any of the programming functionality or any of that stuff in here. What's that?
Set all variables reserved for it.
We could do that. Yep. All right. So anyway, let's go back and start talking about more matrix arithmetic things. So we've talked about how we can add matrices, subtract, do scalar multiplication, do matrix multiplication. We do not do matrix division. We will talk about what we mean by quote unquote division when we talk about inverses in section 3 of this chapter. But right now, these are the only matrix operations that we're going to do. So let's do one more example. Make sure we're on the same page. Let's say our A is, let's just do two square matrices to start with. Let's say A is 2, 1, 3, -1, and B is 1, 3, 2, -4. And I ask you to do A times B, and I ask you to do B times A. I think I used a word a second ago that I haven't defined. If you have the same number of rows as columns, we say the matrix is square. So I have two square matrices here. Both of them are 2 by 2. The reason why I want to do this particular example is notice that in this case, we can certainly do the multiplication in both orders, right? We can do A times B, and we can do B times A. There's no problem with the size of the matrices. Both have 2 rows and 2 columns. So in both cases, the number of columns of the first equals the number of rows of the second. Right? There's no issues with being able to do it. Okay. However, we should notice something happen when we multiply here. What will be the size of the result in both cases? 2 by 2 again, right? The size of the result is number of rows of the first by number of columns in the second. Okay. When we do the first entry, when we do that upper left entry, what do we multiply together? When I want the one in the upper left-hand corner there, what gets multiplied together? 2 times 1 plus the 1 times 2? Yeah. So remember again, to get this entry right here, we'll take this row times that column, right? And so that gives us 4, because we'll get 2 plus 2. How about if we go across to the next one, up in the upper right corner, what do we get? Okay. 2 times 3 plus 1 times -4. So we get 2. We agree with that? 2 times 3 plus 1 times -4. So the 6 minus 4. How about the lower left? 3 times 1 plus what? The -1 times 2, right? Because we're taking, in this case, we're taking, we'll change, no, it doesn't matter. So what I want to do is change the color. That's what I was trying to do. If I want to get this entry right here, we're going to take that row and that column and match them, right? 3 times 1, -1 times 2. So I get 1. Finally, oh, hey, I erased, what was the upper left-hand corner there? It was a 3, wasn't it? It got erased. I don't know why I keep doing that. What do we get for the last entry then? 13? Yeah, I heard 13 a couple of times. Everybody okay with where those are coming from? I know if you haven't seen matrix multiplication before, it's weird. Right? I find it weird. All right. How about the other way? What's the upper left-hand entry going to be? 11, right? So right away, are these two matrices the same? No. In order for the matrices to be the same, they're going to have exactly the same entries all the way across, right? So they're not even the same. Okay. Pardon me. What about the next entry to the right? -2, yeah. Lower left, -8. Lower right, 6. Good. All right, so we're taking row, match it with a column, row, match it with a column, row, column, row, column. So we don't get the same answer here. And that's true in general. Sometimes you do. Sometimes you get lucky and they are the same. There's certain matrices that you can use that will multiply in either order and get the same answer. But in general, matrix multiplication is not commutative. And as a commutative algebraist, I feel impelled to tell you that it's commutative. It's not communicative. You're not a hippie. It's not communicative. It's not infectious. Okay? It's like you're going back and forth to work. Commutative. It's both T's. Okay? Sorry. Just hurts my ears when I hear it wrong. All right. Anyway, not commutative means that you cannot necessarily multiply in either order and get the same answer. We've already seen examples where it may be defined in one way and not the other. It could be defined in both ways and not get the same answer. You might have it defined in both ways and not even get the same size. So what I mean by that is, let's not just if let's say A is 2 by 3 and B is 3 by 2 as far as sizes go. What size does A times B have if you multiply those together? 2 by 2, right? Because again, you match the outer numbers, right? Rows of the first, columns of the second tell you what size it has. How about B times A? What will it be? It'll be 3 by 3. So just because the multiplication is defined in both ways doesn't guarantee you'll get the same size even. Okay? So like I said, matrix multiplication is weird. Lots of different ways that things could go. Right? One of the things that we use matrix multiplication for, to tie a little bit back to systems of equations, is to be able to write a system of equations as a matrix equation. So writing it this way, let's say we have an example where I have the system. Let's say we have 3x1 minus x2 plus 5x3 equals 9. 8x1 plus 2x2 minus x3 equals 7. And let's say we have x1 minus 4x3 equals negative 2. We've already talked about how to write this as an augmented matrix, where we have the coefficients from the variables and then augment the constant pieces, right? But we can also write this as a matrix equation in a similar fashion. We're going to take our matrix of coefficients. So I've got 3, negative 1, 5 as our coefficients in the first equation. I've got 8, 2, negative 1 as our coefficients in the second one. 1, 0, negative 4 is the third one. And our constants on the right-hand side, 9, 7, negative 2, we'll write as a column. So it kind of looks like what we were doing with our augmented matrix, but I literally have them separated now by an equal sign, and I left a gap on purpose. I want to write this as a matrix equation. In particular, I want to write it that looks kind of like a simple one-step equation idea that you saw back in pre-algebra class, right? You had something like 3x equals 9, right? At constant times x equals number, okay? So I want to write it in kind of the same fashion here, but I need my product to be defined. Well, if my product is going to be defined, how many rows does this second matrix have to be? 3, because the number of columns here is 3, right? Agree with that? So the product is going to be defined as have 3 rows. If I want the answer to have 1 column, how many columns can this thing have? 1, right? So in here, I'm going to write a column full of the variables. So we can rewrite the system of equations as a matrix equation. And a lot of times you'll see this written with matrices and vector form. So the matrix of our coefficients here will be A. Ordinarily, when you write vectors, when you write something as a column, we think of it as like a vector, like you do in calculus or physics. Vectors are typically denoted with boldface letters, except that I can't write boldface on the board or the computer very easily. So put a little hat on it, so if it goes outside, it doesn't catch cold. And then the constant part will be another vector with the B. So this is just a way to write a system of equations as a matrix equation. So this is kind of tying together again matrix arithmetic things that we've been talking about with the systems of equation stuff that we've already been talking about. Right? Just say the matrix stuff, the arithmetic stuff that we're talking about today with the systems that we're talking about before. Again, name of the class is linear algebra. We're going to tie as much as we can back to linear systems. All right. We'll do more of this stuff on Monday, as well as start proving some things with matrix arithmetic. In any event, have a good one. We'll see you on Monday. Have a good weekend, everybody.